All right, so here we need to talk about arc length, and then after that, curvature. Now, so vector value functions trace out a curve in either 2D space or 3D space. And back in Calc 2, when it related to functions in 2D space, which essentially represented curves, we talked about how to find the arc length of the curve. And this is really no different. The only real difference here is that the curves are being defined by a vector value function as opposed to being defined by a single variable function. And this could be happening in 3D space as opposed to what we were doing in Calc 2, which was all happening in 2D space. And so the idea of arc length is if I was to travel around this curve here, how far would I be traveling? So it's the distance traveled along a curve is what arc length is about. And so we do it through a series of estimations. So the first way is to think about it as a bunch of straight line distances. So if I start here, I go from here to here, and then from here to here, and then from here to here, moving around 3D space. If you notice, this is happening in 3D space. And I can measure those three distances, add them all up, and that would give me an estimate of the curvature, estimate of the arc length and the distance traveled along the arc. And then what I can do is I can make that a little bit more precise by doing more increments here. So the length from here to here, then the length from here to here, then the length from here to here. And since these are just straight distances, we could use the distance formula to measure the distance between the points. And then we can keep going, making those segments a little bit closer together. So then all these segments, add these up. And what we're doing is getting closer and closer and closer to the actual arc length around here. And so it's basically the distance formula and adding those distances over and over and over again. Well, anytime we add a bunch of pieces together over and over and over again and then let the number of pieces go to infinity, we know that that has to be represented using an integral. And so it's essentially this distance formula added repeatedly. So when we look at the arc length formula, this should look somewhat familiar to you in representing one, the distance formula, and two, the arc length formula we had back in Calc 2 for a single variable function. And so what we need to do is we need to take the derivative of each component function squared and take the square root of it, add them all together, and essentially what that's going to be is really the distance of the x's, the y's, and the z's components of these vector value functions. And ultimately what this really is, if we're taking the square root of x prime squared plus y prime squared plus z prime squared, it's the magnitude of r prime is essentially what we're doing here. And so that would be from a to b, where a to b is the interval of t values that we're using in this vector value function to start here and then to end here. What t value do we use to get from one place to the next? And so to find the arc length of the curve, in this case, this is a 3D curve on the interval from 0 to pi, would be very simple to do. And so what we need to do is we need to find what r prime is, and this should be fairly easy. This will be 2 cosine t, this will be 5, and this will be minus 2 sine t. So that's your r prime. We need to find the magnitude of r prime. So that would be, again, fairly easy to do. So 4 cosine squared t, 25. Oh, let's erase that. Okay, for some reason it's not letting me erase. Okay, so plus, what are we going to have? 25 plus 4 sine squared t, or yeah, 4 sine squared t. We could group these two together and factor out the 4. Okay, so we're going to have 4 times cosine squared plus sine squared. We've done this a bunch of times already now. Plus 25. Cosine squared plus sine squared is 1. So it's really 4 plus 25, which would give me the square root of 29. Okay, so the arc length is the square root of 29. Or sorry, the magnitude of r prime is the square root of 29. So then the arc length should be the integral from, in this case, 0 to pi of the square root of 29 dt. Now, since the magnitude of r prime is a constant, this is actually really easy, but we've seen that the magnitude of r prime isn't always a constant. Sometimes it's a function of t, in which case that whatever that function of t is here, you would have to integrate it. Well, this being a constant is really easy because the integral of constants should just be square root of 29t from 0 to pi. I plug in pi, I plug in 0, and I get square root of 29 pi. So the arc length is square root of 29 pi, but it's not always going to be that simple because sometimes the magnitude of r prime is a function of t. And depending on what function of t that is, we would then integrate it with respect to t. So this could be a little bit more difficult in this example, but nonetheless, it should just be a single variable integral with respect to t, and as long as you know how to integrate whatever function this is, then there's really not much to this arc length formula. Here's another example. Again, same thing. Here's the function that we're working with. We're going to find the arc length of that function between 0 and pi halves. So we'll need to figure out what r prime of t is. This one's going to take us a little bit longer because it's a little bit bigger here. So cosine t would be minus sine t plus, then t sine t would have to do the product rule. So it would be sine t plus t cosine t. So you see these two are going to cancel. And then the next one's going to be sine t, so that'll be cosine t. Then we have to do this integral here again. This derivative. Again, we're going to have to do product rule, so we're going to get what? Minus cosine t. And then we're going to get plus t sine t. So you see these are going to cancel. And then finally, we're going to get 2t. So then we do the magnitude of r prime. Again, shouldn't be that bad. Square root of, well, this is all that's left in the first component, so that'll be t squared cosine squared t. Then this is all that's in the second component, so plus t squared sine squared t plus 4t squared. So if I factor out a t squared out of this, I'm going to get the square root of t squared times cosine squared plus sine squared. Again, that's going to be 1 plus 4t squared. So we're basically going to get t squared plus 4t squared, which would give us square root of 5t squared, which we could simply write as the square root of 5 times t, because we do the square root of each one of these, and the square root of t squared would give us t. So then your arc length should be the integral from, in this case, 0 to pi halves of the square root of 5t dt. Well, again, this one's a function of t, right? Once we simplified this whole thing out, and that would be the key, you want to simplify it, right? If we left it like this and tried to integrate that, that would be a mess. So we're not going to do that. But if we can simplify it as much as possible and get to here, this is a really easy integral to do. Square root of 5 is just a constant multiple, so it's really just t dt. And so that would be the square root of 5 t squared over 2 between 0 and pi halves. So when we plug those values in, we get the square root of 5 over 2 times pi half squared, which would give us the square root of 5 pi squared over 8. Because we square the 2, and then we multiply by this extra 2, and then that's where we get our answer. So pretty easy integral to do again, but that's recognizing what the arc length is from 0 to pi halves on this function. Now this is a much more complicated vector value function than the first one, but you see the process doesn't really change. Find r prime, find the magnitude of r prime, then do the integral of that. And even when it ends up to be a function of t, we could still do it. It's just a matter of, do you know how to integrate? And do you know how to integrate whatever this function ends up being? But the more you simplify it, the better off you'll be before you integrate. And then this last topic we need to discuss is the concept of curvature. One thing you can talk about with curvature is it's really describing how quickly the curve bends, okay? But we could be bending in multiple directions. Now, this picture I have here is just a 2D picture, so it's easier to describe the bend in the curve as you move sort of downward and around. But if we were in a 3D space, okay, your curve could be bending in an XY direction and up at the same time, right? It's not just moving this way, but it's also going upward. So how much of a bend do you have kind of in all directions is what the curvature is talking about. One way to describe this is essentially looking at how rapidly the unit tangent vector is changing with respect to the distance traveled along the curve, which is your arc length. And so if we look at, say, all these unit tangent vectors, think of all these purple arrows as the unit tangent vectors. Looking at the change in these unit tangent vectors and how quickly they're turning with respect to the distance traveled is really the concept of looking at how the curve is bending, okay, and how quickly that curve changes direction at a particular point. So if we look at the change in the unit tangent vector with respect to arc length, that's what we're going to describe as the curvature. So the K will be our variable we use for curvature, not C, because C represents the curve itself. So we're going to use K to represent curvature. But it's really the change in the arc length, with change in the unit tangent vector with respect to arc length. So you see this here, as opposed to, maybe if I had a circle instead and I was looking at the unit tangent vectors changing direction. If you see in here, the unit tangent vector is going to change its direction more rapidly right here in this section of the curve as opposed to maybe in this section of the curve. And that's because the curve bends here a lot more than it does over in this section. And so that's what curvature is going to be all about. Now there's a couple of ways we can calculate this curvature. Yes, it's the change in the arc length with respect, or change in the unit tangent vector with respect to arc length, but to really use that and to find the actual value using this calculation, we can be done in two ways. This is the first formula, which would make more sense in terms of what the definition is. Right? If we're talking about the change in the unit tangent vector, it should be the derivative of the unit tangent vector. With respect to the arc length, should be the change in the arc length. So this should make more sense in that definition, in that we're going to do the magnitude of the unit tangent vector divided by the magnitude of r prime. But that's not always useful in practice. So then we always have I shouldn't say always, but we have a second way of calculating the arc length using this cross product divided by the magnitude of r prime cubed. Now, when you decide to use each one of these formulas really depends on what happens to the magnitude of r prime. This is really the deciding factor. What kind of value do we get out of this? And we've seen this multiple times in that sometimes the magnitude of r prime is a constant, and sometimes the magnitude of r prime is not a constant. It's a function of t. And so this right here is the determining factor as to which one of these two formulas we should use. If the magnitude of r prime is a constant, then this formula right here is definitely the easier one of the two. We would want to, because trying to find the magnitude of t prime, which would involve finding the magnitude of r prime, is going to be important. So if the magnitude of r prime is a constant, then this is a fairly easy formula to do. However, if the magnitude of r prime is not a constant, then this is going to be the better formula to use. It'll save us some time in our calculations. The computation just becomes much less. And you would think, well, oh, this is a cross product, so maybe not going to be that easy. But if the magnitude of r prime is not a constant, this actually does still end up being easier, even if we have to do a cross product. A couple of things you need to know is that in the end, the curvature is always going to be a real number. It's going to be a scalar. It's going to be a constant at a given t value. The curvature for the entire curve itself may not necessarily be a constant in the end. It may be a function of t, which just tells us that the curvature at each point will be different. And you could see maybe with something like this that the curvature would be different here as opposed to here, because the amount of bend in the curve is changing, right? So you expect most curves to have their curvature throughout the entire function to be a function of t, but at a particular location on any curve, the curvature right there will be some scalar, okay? It will be a constant. One thing that will happen with a circle is that it's turning the same amount the entire time. So the curvature throughout the entire function would end up being a constant. It's always going to be the same no matter what the point is in a circle, And we could easily find it simply by just using 1 over r to find it. But we could also see that we're going to get the same thing if we use this formula. All right, so let's look at an example and see how we use the formula to calculate the curvature for a given function. And again, this would work whether it's a 2D curve or a 3D curve. It's just a curve that has to be defined by a vector valued function. That's really the only thing here. And in some ways, this is a little bit related to what we looked at in 2D, where we talked about the idea of concavity. Okay, concavity told you about the turn, right? How much, whether we're curving upward or curving downward, and to what degree we were doing that. So that concavity idea and curvature are somewhat related here. But we can extend this into 3D as well, and we use this for not just functions of a single variable, which is what we did with concavity, but we can also do it for these vector valued function curves. So to calculate the curvature, the first thing I want to do is find r prime and then the magnitude of r prime. Because I'm going to need that for either formula that I use, but what happens here will then determine which formula I use. So first r prime, which should be easy to find at this point for any vector value function. We've done this enough times now. So in this case, this one is one we've seen repeatedly. So 3 cosine t minus 3 sine t and 4. And then we're going to find the magnitude of r prime, which would be the square root of 9 cosine squared t plus 9 sine squared t plus 16. And again, we've done this a couple times now. Factor out the 9. We have cosine squared t plus sine squared t plus 16. So we get the square root of 9 plus 16, again, because this is 1. And so we get square root of 25, which is just 5. So this is a constant. And since that is a constant, I'm going to use the first formula for curvature, which is the magnitude of t prime over the magnitude of r prime. And we already have the denominator, which is 5, so we just have to find the magnitude of t prime. Well, in order to find the magnitude of t prime, we have to figure out what t is first. So t of t, remember, is r prime over the magnitude of r prime. Well, we have that here, so this would be the square root, this would be, this vector here divided by 5, so we could just say 3/5 cosine t minus 3/5 sine t and 4. And then we have to find t prime, which would be negative 3/5 sine t, negative 3/5 cosine t, and 0. That would be the derivative. And then we need the magnitude of t prime, which would be the square root of 9 over 25 sine t, sine squared t, plus 9 over 25 cosine squared t, plus 0 squared, so just this. Factor out the 9 over 25. You get sine squared plus cosine squared, which is 1, so we get the square root of 9 over 25, which is 3/5. Okay? So then our curvature would be 3/5 over 5, so 3 over 25. So the curvature, remember, notice we didn't do this curvature at any specific point. This is just the curvature for the curve at any t value, and we got a constant for that. So that means that this thing has got the same curvature everywhere. Well, we've talked about this curve before now. This is essentially our helix that's going like this. It's a circle. The rise is rising at a rate of 4t, and the curve is turning around this circle here. Radius 3 in this point because of 3 in front of the sine and the cosine. But nonetheless, if you see that this thing is turning at the same rate the whole time. If this was, say, not a 4t, let's say that that was a t squared. Well, what will happen is that this gap in between the curves this way, the amount it's rising along the z-axis, would be rising at a quadratic rate instead of a linear rate, And so this distance here would get bigger and bigger and bigger as I went up. So it would look more maybe like this, and then like this, and then like this, and then like this. In which case now it's not curving at the same rate as I go upward, right? As I move along this, I wouldn't expect to get the curvature to just be a constant. It would probably be a function of t, so that in this location, or this location, or this location over here, I would be getting a different curvature. But that's not the case in this example. We did get a constant curvature. And notice that the magnitude of r prime being constant is really the key to this whole thing being not so difficult computationally. Because this is a constant, finding t is a little bit easier, and then therefore finding the derivative of t is definitely a lot easier, and then the magnitude of that is done. If this was not a constant, trying to compute the derivative of t, the unit tangent vector, would be far more difficult, because this would be a function of t here and here, and I screwed up, but it doesn't really make a difference. This should have been over 5, but still the derivative of it would be 0. But anyway, this would be a function of t here, here, and here, in which case when I took the derivative of this piece to get this, I would be using the quotient rule, and then here this would be t's over t, so that would be quotient rule to get here, and same thing here. This would no longer be 0. So finding that derivative and then the magnitude of that would be really difficult computationally, which we've talked about a couple times now. But because that didn't happen, this was a fairly easy formula. But that's where we have that alternate formula we could use when this is no longer a constant. Sometimes that's a function of t.